上礼拜感冒还没有完全好，所以今天就戴口罩上课。那今天有2位贵客，一位是这个经济系的郑教授来给我们指导然后另外上礼拜来过来观察这个光武上课的情形。那希望到时候能够这个得到一些建议好，那接下来我们就转换到我们的英语频道那个，今天上课人数好像比较少，是因为观课把大家吓坏了吗？是？好，没关系。好，那我们就开始我们的上课内容。So let me summarize how we have learned up to now in chapter 4. First, we consider the so-called anisotropic medium. An anisotropic medium means that in Maxwell equation, the relation, the dynamical variable d, we know that the dynamic variable d is related to p and p by this relation. And when you are given a medium in the fundamental course of electromagnetism, you can write this as epsilon times E. So in the simple case that this epsilon is only a real value. If the medium is something like air, water, glass, you can always assume epsilon as simple as this. However, in a crystal, for example, calcite, the situation becomes more complicated. That is to say, in general, a crystal has some specific directions, which means that if you apply electric field to the crystal, for some direction it is easier to polarize this medium, but for some other direction it is harder to polarize this medium. So this factor leads to the result that in general, P in general is not parallel to E. E is the applied field. So this leads to the similar result. The D field is also, in general, not parallel to the E field. Okay? So mathematically, we want to express the linear relation between D and E. So we must generalize the original idea of epsilon from a simple number to a thing called tensor. Okay, the mathematical description of tensor can be matrix. Okay. For our purpose to describe crystal, this property is called permittivity. The epsilon becomes epsilon matrix or epsilon matrix. The epsilon matrix, I can write it as this form. Okay. If you choose a proper coordinate system， 进来啊！你有没有走错教室 ？OK 啊。If you choose you can rotate your coordinate system to make the representation of this epsilon tensor different. Okay. You can always find a coordinate system that the epsilon tensor becomes a diagonal form. So it becomes the form. In fact, that so-called correct coordinate system, the three coordinate axes are just the eigenvectors of the matrix. Okay. So if we work our problem in this correct coordinate system, everything becomes simpler. And we call the three coordinate system, three axes of the coordinates, this special, very special coordinate system, principal axis. Principal axis 主轴，主轴。那光学上要描绘主轴的话，我们更方便的方式是用折射圆。In optics, we know we have another quantity called mu0 vacuum permeability. These two quantities, the product of these two quantities, here epsilon 0 is the vacuum permittivity, is equal to 1 over c squared. In this textbook, I have told you that although the author always used the symbol mu, but the symbol mu in fact means mu0 because we consider only non-magnetic material. Okay. Here c is the light speed in vacuum. Okay. According to this notation, we can define three reference refracting indices. We define nx squared as epsilon x over epsilon 0, ny squared is defined as epsilon y over epsilon 0, and nz squared is defined as epsilon z over epsilon 0. Through this definition, and we work in principal coordinate axis, then the epsilon tensor can be represented as epsilon 0 times nx squared 0, 0, 0, ny squared 0, 0, 0, nz squared. Okay. So we use this expression of epsilon and discuss what happens if we consider wave propagating inside the crystal. So according to Maxwell equation, these four Maxwell equations, okay, and we consider the complex expression of all the quantities we have already introduced the concept of complex representation of these physical quantities. The purpose of complex representation is that for the exponential form, it is easier to do integration or differentiation. Okay? Because if you consider cosine of sine, the differentiation of cosine is proportional to sine. And you must do the same operation once again, then you get the original cosine. Okay, but for exponential, every time you do the differentiation, you get a result proportional to the original result. So this property tells you that use complex representation, you can change the differentiation or integration by algebraic multiplication， 就是变成是一个代数上的乘法。So using this property, when you encounter something like this, you can express the result as this. Okay. And then when you encounter something like this, then this becomes minus ik. And if you here, if this is a vector field, here is a plot or cross, then here is a dot or cross. Okay. Then the Maxwell equation tells us that the first equation tells us that K dot D is equal to 0. The second equation tells us K dot D is equal to 0. Okay. And the third equation tells us that K cross D is omega D. And the final equation tells us that K cross H is minus omega times D. Remember, D is related to population, and you can just identify it as this. So this means that K dot H is 0. Okay. And notice that here, this is the tensor or matrix. So according to this result, when we consider the EM wave propagating inside the crystal, suppose this direction is the direction of wave vector. Then we know that here, D is perpendicular to K, and H is perpendicular to K also. And this equation tells us that E is also perpendicular to H. Okay, and K cross H is proportional to D. So this means that these three vectors are perpendicular to each other. And how about the E vector? In general, E vector look like this. E belongs to the plane of K and D, which means that we can write E as some coefficient times K plus some coefficient times D, something like this. And this tells us a very important result. The result is that when we consider Poynting vector means Poynting vector is E cross H. We have already learned that K is the propagation direction of the phase of the wave, and Poynting vector is the propagation of energy. Okay, so Poynting vector means energy current density, energy per unit time per unit area. Its direction is determined by this. Okay, and you can show that the angle between P and E is the same as the angle between K and S. So in general, in a crystal, if you consider electromagnetic wave propagating inside the crystal in arbitrary direction, then in general, the phase propagation direction and energy propagation are along different directions. Okay, say, suppose this is the direction of Poynting vector, and constant phase. This is the direction of K. Generally, they have different direction. Okay, and so usually we say electromagnetic waves are transverse waves. In what sense we say that the wave is transverse? If you are talking about E field, that is correct. D is perpendicular to K, so it is transverse wave. However, if you are talking about E, this is not certain， 就不一定啊。在 crystal 里面的话，其实你如果要看 K 跟 E 的加长，它就不一定是这样。Arbitrary 的时候就不是。So this tells us that the propagation characteristics may have some usually is dependent on the propagation direction. 好，所以就是说，这个传播的方向会跟它的这个一些特性有关。什么特性呢？我们最重要是要所谓的折射。So usually in isotropic medium we have a fixed refractive index. For non-magnetic material, refractive index usually is given by this formula, epsilon r square root of epsilon r. Here epsilon r means that epsilon over epsilon 0. However, in this anisotropic medium, what is the refractive index? Now the refractive index becomes direction dependent. Become direction dependent. To solve for to find the equations to determine the refractive index, we use these two. We use these two Maxwell equations, or its equivalents, these two equations. So according to these two equations, we have already derived the so-called Fresnel's equation with normal. It looks like this. Here S is not pointing vector. Here this S is the three components of the unit vector small s. What is small s? Small s means this. The K vector can be written as omega over c times refractive index times the propagation direction unit vector. Okay. So you use this ansatz and substitute it into these two equations. And you can find a linear equation like this. You can find an equation look like this. And this matrix cannot have non-zero determinant, because if it has non-zero determinant, we can construct its inverse. Then if we multiply the inverse matrix, we get zero E field. However, we want to find the E field inside this medium. It cannot be zero. So this implies that the determinant of this matrix must be zero. And this zero determinant relation gives us Fresnel's equation of wave normal. And this equation, in fact, if you multiply the equation by this factor, this factor, this factor, and remember that 1 can be replaced by sx squared plus sy squared plus st squared. Okay, then you will find that the final result is the equation of fourth power quadratic equation. Okay. Then you can solve for n squared. You will find B is negative, A is positive, C is positive. And this in fact is equal to this. Okay. So for a given propagation direction, you solve for refracting this, and you get two possible refracting this. So if I denote these two refracting indexes as n1 and n2, then I can have K1 and K2. K1 and K2. This means that for a given frequency, if you plot all possible propagation direction, for all possible propagation direction and all possible refracting indices, you will find a structure the surface look like this. 这个只画出了1/8啊。We have a double shell surface. Okay. In the first octant, it looks something like that. 我昨天有寄了一个 MATLAB code 给大家，让大家可以自己去玩一玩。So yesterday I have sent a MATLAB code. You can use the MATLAB code to plot this double shell surface. This double shell surface is called normal surface. So normal surface means that for a given direction, you just choose your direction. Then you draw a line along that direction. Then you get two possible intersections with the double shell surface. These 2 points correspond to these 2 possible K vectors. Okay. So in a general anisotropic medium, you have 3 principal axes. Okay, and you have the normal surface to describe how the refracting is related to the propagation direction. Then we can use normal surface to find the wave's group velocity or energy velocity. Okay. I have already explained that in general, the energy propagation direction and the phase propagation direction, usually they are different. Okay. And for beam of light, the beam direction is the energy propagation direction, or the direction of the pointing vector. Okay. So, how to find this direction? Mathematically, we know that if we have a surface, the surface, I denote it as omega of k. We treat k omega as function of k. This function is called dispersion relation. Here, omega of k is just our normal surface. Then, mathematics tells us that gradient omega Gradient omega is perpendicular to the surface. Okay, of constant omega. Okay, we have this relation by But if we let this to be some specific frequency, then corresponding to this specific frequency, this means that our normal surface, then gradient omega is perpendicular to this surface locally, and gradient omega is just velocity. Here, this gradient means we replace the original definition of gradient. The variable x, y, z are now replaced by kx, ky, kz. Okay. This notation means that所以这个是 k 空间中的梯度，啊 ，k 空间中的梯度就是什么？就是曲速度啊。The gradient in k space. So we know that the light energy propagates along the direction that propagating perpendicular or orthonormal to the normal surface. Okay, so we can use this factor to predict the propagation direction of light. That's what we have called last week. Okay. 但是我上礼拜还没有完全教完，所以我现在可以连上上礼拜所教的东西，再继续。So, if we now consider the problem of refraction, and the reflection, consider light, incident light, and we can calculate the reflection and refraction rate. In the usual isotropic medium, we have something called Snell's law. 这边的 N1、N2 是 isotropic 介词里面的 N1、N2， 我们等一下再解释 N isotropic 介词时候会变成怎样。So, if we consider isotropic medium from medium number 1 to medium number 2, they are separated by this interface. Consider a beam of light incident from the medium 1 to medium 2. Then we have the so-called Snell's law. You have at least two ways to derive this Snell's law. The first way, you learn in geometry optics, the geometric optics tells you that you can find the path of light by using so-called Fermat principle. Okay, Fermat principle claims that light always propagate along the path that take the shortest time. Okay, and in fact, light does not take this specific shortest time path. The result seems like that, but the reason is in fact constructive interference. Okay, because the reason of constructive interference, only the shortest time path result the light energy constructive interference with the nearby path result, and we see very clear beam. If you consider the direction of path deviated from the correct one a little bit, then destructive interference becomes too large. Then you will not see clear energy aggregated there. So finally, you will find a clear path, just like light choose the shortest time path. You can consult what I said here by a small book called QED, The Strange Theory of Light, based on Richard Feynman's lecture, okay, in New Zealand. Okay. And another way you can find this Snell's law. You can use your electromagnetics knowledge. Okay. Then, based on the boundary condition, if you consider the tangential component of the E field and H field, they must be connected on the two sides of this interface. And since we assume they have the form of plane wave, so this implies that the phase must be continuously connected on the two sides. So suppose this direction is named Kx. Then this implies that K1x is equal to K2x. Okay? And since K1x is N1 omega over C times sine theta 1, and the K2x is N2 omega over C times sine theta 2. Then from the result, you can conclude that N1 sine theta 1 is equal to N2 sine theta 2. This is the Snell's law. Okay. In anisotropic medium, the result becomes more complicated. But the same kind of condition still hold. Okay. So if you consider this situation, here, crystal. Okay. So if I plot the normal surface, it's a double shell structure. Some orientation, it may look like this. And we can also plot the normal surface for light in air. It's just a very usual sphere. So suppose here is the origin, and this vector indicates the incident light K vector. Okay. I denote it as K0. So to keep the horizontal components of K vector unchanged, we know that the projection of K0 is this. So we plot the same line here and plot the vertical line. Okay. So you see these 2 points correspond to the same projection. So you have this and this. Okay. So here this I denote it as K1 and this as K2. Now we have 2 different K vectors. Okay. These 2 different K vectors is not the original K1, K2 corresponding to the same propagation direction, but now it corresponds to the same projection, this horizontal component. Okay. So you can predict how light refraction along what direction according to this graph. So you see, I take the normal vector of this and take the normal vector of this. So we can predict that for a light beam incident along this direction, the refraction, we have 2 refraction beams along this and this direction. Okay? We can apply this idea to a single case, the so-called uniaxial crystal. Uniaxial. Uniaxial crystal means that the 3 reference refractive indices, 2 of them are the same. For example, nx is equal to ny equal to no, and nz equal to ne. Now,好，我这边先停在这边，我们先下课10分钟，再继续。